Okay, thank you. Hi, everyone. I welcome all to the Mobility Engineer 2030, a Mahindra Technology Leadership Talk Series hosted by NPTEL. So let me share my screen. So the title of this talk is Multi-disciplinary Design Optimization in Automotive Engineering. So before starting, I would like to thank Dr. Shankar Venugopal, Vice President, Mahindra Research Valley, and Dean Mahindra Technical Academy for giving me an opportunity to share my thoughts on this topic. And this is talk number 2. You can see here, this is talk number 2, titled Multidisciplinary Design Optimization in Automotive Engineering. A brief introduction of myself. So I was with Mahindra and Mahindra from 2000 to 2005, and then again in between I went into various other product development organizations like Sonalika, GE, and then again I was back to Mahindra Research Valley 2016, and I'm here. Then presently I'm heading technical capability building of automotive division at MRV. And my education qualifications, I'm master's from IIT Kharagpur and Ph.D from Indian Institute of Science. Thank you. I am also an adjunct faculty at Virginia Tech, India, where I teach industry-specific case studies on how data science and AI can be applied to automotive product development. Today, I will take you through these contents. We'll start with why optimization, what is optimization, and what is MDO. Then we'll go through applications of MDO in automotive domain. Then we'll see what are the key challenges in applying MDO. Then we'll also see the benefits of MDO. Then we'll come to a very important topic on lightweighting. What is lightweighting? What is automotive lightweighting? And what are the advanced MDO strategies for lightweighting? Then we will see machine learning based lightweighting and what are the disruptions because of advanced AI and ML based algorithms, what kind of disruptions are happening in CAE workflows. And I will end this with a learning map which will act as a career guide for anyone who want to start the career in MDO. So why optimization? So optimization, obviously it improves design quality. So in the context of automotive design, so when we're talking about design quality, customer perceived quality, fit and finish, drivability, ride and handling, durability, safety, so on and so forth. So when we try to use optimization algorithms at different levels in the automotive product development cycle, we will come up with a product which will meet the quality requirements. And then one more very important aspect in an industry context is meeting a project's time, cost, and performance targets. Many times what happens? Because the automotive system is very complex, you have a lot of conflicting requirements, which we will see in the next slides. It is very important for us to optimize the systems considering various conflicting requirements, and we have to take decisions, trade-offs at different phases of the product development. And these decisions have huge impact on time, cost, and performance targets. So how do you use this optimization to ensure TCP targets? Then the other very important thing is these optimization algorithms will help engineers to come up with novel concept, innovative design solutions. And since the number of iterations will come down because we are trying to front load optimization in the very initial stage of the product development, since the number of iterations will come down, so the engineers will have quality time to spend, they can spend on coming up with innovative concepts, right? So this is very important. So 3 things: improves design quality, assists in TCP targets, and then helps engineers in innovation. Now we will see what is optimization and what is MDO. So optimization is the process of obtaining the best results under the given circumstances. So given circumstances in the context of automotive product development is circumstances in terms of timelines, in terms of engineering requirements, conflicting engineering requirements, circumstances in terms of cost aspects. So how we trade off all these things and then come up with an optimal solution, right? So the goal of a problem is either to minimize the effort or to maximize the benefit. Let's say we want to, okay. Now, if you look at, for any optimization problem, there will be an objective function. Let's say we minimize f of x. X is a vector. Right? It's a vector having a lot of design variables. In the context of automotive, this x can be a vector of thicknesses, thickness of components or material properties, so on and so forth. And then there are some constraints, right? These constraints, if you talk about automotive, these constraints can come up from various disciplines. Let's say fluid dynamics, right? We want to reduce the coefficient of drag to improve the range of an EV or any IC engine powered vehicle. So there is a constraint from fluid dynamics. You have to do a lot of fluid dynamic calculations. And then constraints, design verification plans come from durability aspect. You need to meet the damage. You need to meet the fatigue life and reduce the damage at critical locations, right? And then there are some regulatory requirements coming up, and there are some occupant safety requirements which, as an OEM, we need to take care. So how do you capture these constraints from crash? And then there are some NVH requirements with respect to ride, handling, noise, comfort, so on. Typically, in any OEM, there are experts in each of these areas, right? And these areas will go on extending in a real product development. Like, for example, you need ergonomics, you need to take care of ergonomics requirement, right? You need to have an aesthetic styling. So there may be multiple requirements, and experts are there in each area. So how do you capture the requirements coming from these domains, these disciplines, and then formulate an optimization problem, right? And then come up with a set of design variables, x1, x2, x3, right? Optimal set of design variables, which will meet these constraints coming from various disciplines, and then minimize the objective function, right? So this is what MDO is: multidisciplinary design optimization, because a lot of disciplines are involved, a lot of multi-physics problems are involved. If you see the physical interpretation of this, let's say that if this is a hill and then somebody has to get into the peak, right? The objective is find the highest point. And then you have design variables. Design variables are the coordinates, longitude, latitude. And then you have also constraints here. Constraint, what is this? Stay inside the fence, right? This fence is a constraint. Somebody can start here outside the fence, and then the algorithm will start and find out the gradient, and then go towards the objective function, right? Now the question is, the solution can be this point, the topmost point can be the solution when there are no fences, when there are no constraints. But given the fences, given the constraints, then your optimal solution would be the point where there is a red flag, right? So your solution, your objective function solution should meet these constraints. Typically, these constraints, these fences are nothing but those constraints which come from durability, from crash, from ergonomics, so on and so forth. So this is how you can actually have a comparison. Now I'll talk about application of MDO in automotive domain, right? We'll dig little deeper into why do you need MDO and applications. So if you see suspension design, right? So if I take a turn, and when I'm taking a turn, I need lateral stability, and my suspension should be suspension should be stiff enough so that I will not have the stability problems. I will not have the handling. But if you make your suspension stiff and improve the ride, then it may result in lowering comfort, right? When there is a stiff suspension, then the vibrations are transmitted to the occupant. So how do you balance these two requirements, right? Drivability. Then let's say you are designing an HVAC system where your objective is to give thermal comfort to the occupant. There are vents, there is airflow, and different depending upon the ambient temperature. So you want to maximize the comfort. But then it also has an effect on the fuel economy because the power consumption of various auxiliaries to drive the HVAC system, right? They consume power, consume energy, and this is fuel consumption. So how do you optimize this system? And now if you look at the right-hand side, typically when I design a pillar, if you see the A pillar is something here mentioned A pillar. So when I go for an aerodynamic requirement to reduce coefficient of drag, my A pillar angle with respect to horizontal should be as minimum as possible. Then only the coefficient of drag will be better. But then when there is a rollover, right, the crashworthiness will go for a ride because it cannot absorb the energy. It will directly transmit to the occupant. Right? There's a conflicting requirement. Also, when you try to design an A pillar for better aerodynamics, then you may have to compromise on the occupant space inside, right? There may be some ergonomic issues. Now we can also see certain other conflicting requirements like durability versus crash. You can see here durability, a tough terrain, real world usage pattern, and a lot of fatigue loads are acting on various structures of the vehicle. Now somebody has to meet this fatigue requirement, then their gauges should be thick enough, right? Thickness of the structure should be sufficient, metal property should be sufficient to minimize the stress. But now for the structure should be crashworthy, it should absorb energy. When it absorbs energy, then the energy coming to the occupant will be less because the structure has absorbed and the G levels coming on the occupant will be less and occupant will be safe. So you need to have a structure which crushes, which absorbs energy. Further, the thickness requirements are different. For durability, the thickness requirements are different. So how do you manage this? Right? And for NVH, the thickness requirements are different, or geometry requirement or the metal property requirement is different. So how do you manage this? And another important aspect is, let's say you're coming up with a interior trim design, right? A pillar, and so again A pillar, there is a seat belt, but there is no airbag. So in case of an accident, there is a chance that the head will impact the A pillar, right? So so what happens? A safety engineer will try to design some foam type of structures or foam type of structures or some elements which will break when there is a head collision to absorb the energy and reduce the impact on the head. But all these things comes with the space inside the occupant. So you will occupy space when you are designing this safe system. So there is some compromise on the ergonomics. So how do you deal with this? And the last one in terms of conflicting requirements, let's say somebody wants to design a piston bowl which has the best efficiency, combustion efficiency. For good combustion efficiency, mixing is very important thing. Turbulence is very important. To have good turbulence, you can design a bowl with a very good turbulence, right? By improving the re-entrancy ratio. When you are doing so, there are chances that you may lose the wall thickness. So when you lose the wall thickness, obviously, piston is subjected to firing loads, firing pressures, and a fatigue cycle. Then there are chances that it may have a thermal fatigue crack during its service. So how do you manage combustion efficiency and thermal fatigue, right? So typically, these are some of the things, and this list can go on in a real world product development scenario. And these conflicts need not be these two. This can be a list of conflicts, and all these conflicts are happening simultaneously. You need to manage these conflicts, right? So now let us look at key challenges in applying MDO. So now that you know what is optimization, what is MDO, what are the applications of MDO in automotive product development, what is the need for MDO. Now we will look at what are the key challenges when somebody wants to really use this MDO concept, right? First, phase one, when start of MDO. Formulation of the problem requires multidisciplinary knowledge. So when somebody is trying to formulate mathematically constant equations or the objective functions, then he should understand all domains. He should understand the ergonomics, come up with the ergonomic design rules. He should understand the durability aspect, fatigue aspects, right? Real world usage pattern aspects. He should understand the regulatory requirements coming from crashworthiness. He should understand the vehicle dynamics requirements. He should understand the stiffness requirements of a BIW structure, longitudinal torsional stiffness to meet the NVH constant. You should also understand the noise part of it. So there are multiple domains which are there. So in the initial stage itself, an engineer, when he's trying to formulate a problem, he should have a breadth across multiple domains and specialization in his own domain kind of algorithms, kind of how you mathematically represent the complex problems, engineering problems. That's one. Now, let's say you formulated the problem. Now you want to run the MDO, right? So MDO, you need to have exposure to many software tools because there is no single tool which will do all these multi-physics problems. There's no single tool which can do all this run at the same time. So you need to have exposure to various software tools, right? Like LS-DYNA for crash, ANSYS for various thermal structural problems, ADAMS for vehicle dynamics, BACS for contact problems, GT power, 1D simulation tools for various modeling, combustion modeling, so on and so forth, right? So using tool is also very good. So how can you find somebody who is having at least breadth across all these tools, and he's also expert in one particular tool, like optimization toolbox. Let's say you got a person who got into this. Now, once you get the results, like you got result, like say you got an optimal solution, right, in terms of either material property or thickness or a shape or whatever distribution of material in the structure. So how do you ensure that this is manufacturable, and not only manufacturable, your proposal will also help, when somebody is trying to do service, right? You have various options, right? Which is manufacturability, you'll take care of design for assembly, design for service, design for cost, and also you look at scalability aspects and recycling. So how one can convert this solution which is coming from these algorithms, softwares, to make it reality. So it requires a lot of adjacent areas, knowledge in adjacent areas, right? So these are some of the key challenges in applying MDO. So organizations will try to actually develop teams like task force of MDO, like huge teams, because this is very critical. OEMs are looking at a system as a whole, not in so when you try to look at a system as a whole, you need the specialists in MDO specialists. Now coming to, once you know the challenges in MDO, what are the key challenges in automotive lightweighting and benefits of MDO, right? So I will tell the significance of lightweighting in the next slide. So in this slide, I'll tell how the MDO is, we can benefit from MDO. So let's say, when you're trying to do lightweighting, there are huge number of design variables, right, in an automotive, and huge number of constraints, which you saw in early slides. So MDO can handle this huge set of design variables and constraints, right? Objective way. Then highly nonlinear multi-physics problems, crash problems, right? Now, if you apply machine learning, right? If you come up with predictive models using machine learning for especially nonlinear problems like crash or fluid dynamics, right? With some accuracy, practically required accuracy, right, for that design problem, then you can use those algorithms in combination with the MDO, right, and reduce the time required, to solve to come up with the optimal solution. Highly nonlinear problems can be tackled easily. And of course, there is no single solver that can do MDO considering all domains. So if you can come up with your own MDO solver, which can integrate all these softwares and then simultaneously run all these softwares and then come up with the optimal solution. So that's possible with a lot of MDO solvers. Then of course, huge computational time and cost can be saved when you come up with when you use an MDO, machine learning based MDO, right? We will see some case studies based examples in the coming slides, right? Now, so if we talk about lightweighting, so this few minutes I would like to spend on why lightweighting is required in the context of automotive product design. So if you look at current technologies, IC engine-based technologies, right, stringent emission regulations are coming up. So definitely when you lightweight, let's say you reduce 200 to 50 kg in a vehicle platform, definitely the emissions may come down. Provided, what I mean by emissions can come down is you can actually use can derate the engine, right? When you derate the engine for the same acceleration performance, right? For the same acceleration performance and the load carrying capacity, you can use a slightly reduced horsepower engine, right? And that will affect in reduced emissions. And it has an effect on the fuel economy because the weight is less. Right? This is with respect to the IC engine powered vehicle. Now, when you talk about next generation technologies like electric, autonomous, and connected, and one very challenging thing is range optimization, right? So how, because in Indian conditions, in Indian traffic scenarios, even if it's a city ride, right, a lot of traffic is there and a lot of signals are there, and then you need to have a acceleration, deceleration multiple times. So how do you manage the required range? Right? For that, lightweighting is very critical. So now, once we know this criticality of lightweighting, and OEMs are taking very seriously on this lightweighting. So there are various sources in which, in an automotive, you can get into lightweighting areas. One can be a material focus, where you can come up with the high specific strength steels, of course, meeting the cost requirements, composite materials, right? Foam type of materials, and distributing materials at different locations, right? Based on the CAE solution. So you can actually leverage on the material. And also you can come up with various joining techniques. Let's say you go with a additively bonded joint for a head section. Let's say there is a head section, 2 head sections, you want to join it. You can either spot weld or you can have a bonded joint, right? So let's say in a bonded joint, let's say the crash worthiness is better, let us say. Then you can reduce the, you can have a potential to lightweight. So joining techniques also will have an influence on the lightweighting aspect. Then engine downsizing. So when you downsize an engine for a particular application, definitely there is a potential for lightweighting. And when you talk about engine downsizing, right, we need to also take care of all the other requirements in terms of durability, NVH, right, and other requirements which are coming because of the engine power rating. Then there is another very important thing which our focus of this talk would be on this design optimization through wall thinning or size optimization or shape optimization, topology size optimization. This is purely through CAE and through size optimization, design optimization using CAE. Then any other type, I'll not get into that. It's slightly different. So now the focus of this present talk would be on this box, design optimization, right? Wall thickness or thickness, size optimization. So typically, a vehicle weight distribution, if you see, it's on 34% of the weight typically is on body systems. And if you see DAC systems, electrical, trims, thermal systems, powertrain systems as the other spread. So the sweet spot or the low hanging fruit is, for lightweighting would be body systems, right? BW structure. So what I'll do is, I'll try to show an example, right, on automotive lightweighting, and I will explain various CAE methodologies which are used, right, and I will show how the methodologies are evolving, right. So this is a simple problem where the in automotive there is a very complex problem, a lot of design variables there. For simplicity, I took only these 3 components, right, bumper beam, left front rail, and left shotgun. These thickness T1, T2, T3 are the design variables, and the objective function is the minimization of mass. And constraints in real life, the constraints can come from various domains which we saw, and also the constraints, right, and a lot of design verification planes are in place, right. But for simplicity, I took 3 constraints here, one coming from the NVH, natural frequency of the system, one on fatigue life, and one on peak deceleration. Peak deceleration less than 43 G. This is a safety constraint. If the peak deceleration coming on the occupant is less than 43 G, the occupant is safe. Thought to be safe, right? So, and these are the finite element models, one corresponding to NVH, one corresponding to durability prediction, right, and another corresponding to crash. So this is the background. So here we have only three: NVH, durability, crash. And NVH is fairly a linear problem. And even the computational time will be less when you try to solve an NVH problem. And durability problem, durability analysis is also, it can be linear, it can be non-linear. When you actually model the material non-linearities, it becomes non-linear. But let's say you model well within the elastic limit, then it's also straightforward, and durability also will take less time to solve using computation, even a full vehicle level analysis. But the crash analysis is very critical because non-linearities pertaining to material, non-linearities pertaining to contact, right? And non-linearities pertaining to geometry. Right? So all these three non-linearities, with all the components in place, full vehicle, it's a very time-consuming and tedious process, crash analysis. So the key is, if you, in an intelligent way, if you try to reduce the number of crash runs, then you are in game in an automotive optimization problem, right? So how do we do this? So there are various ways. So I will start with response surface based method, which I know most of you are aware. And then we'll go to a practical MDO, which is Professor Anindya Deb, Professor Deb and myself. When I was at IISc, we came up with this method. Professor Anindya Deb was at that time, he was my research supervisor. And then we have hybrid MDO, right, which is a combination of practical MDO plus equivalent static load method, right? And equivalent static load method is Genesis does that, right? I will talk about this. And then we have machine learning based MDO. So I will show you how we travel from RSM based method to a machine learning based method and how it will affect the project's time, cost, and performance. So just thought, not so mathematically rigorous, just thought to represent a response surface. We all know the response surface, simple response surface. Let's say T1, T2, T3, three-dimensional. But in real world, response surface have multi-dimensional. And it's very difficult to visualize. Let's say you have a response surface. And let's say you have a plane representing a constraint equation. And let's say for your problem, the feasible region is this, the arrows decided. Then if somebody wants to come up with a minimization, right? Minimization of the objective function, right? Then there will be a solution which somebody can find out in the feasible region. But let's say there is no plane here, there is no constraint equation, then obviously the minimum point is, right? Objective function minimum is here, and the variables corresponding to this point is the optimal solution if there is no constraint equation. If there is a constraint equation, then there is another point, right, which the algorithm will figure out. This is typically response surface method. So how this response surface method is applied in optimization problem, automotive optimization. So you first start with a populated DOE, design of experiments, and you do NVH crash and NVH durability and crash for all the DOE points, right? And when you do NVH crash and durability for all these DOE points, you can come up with the predictive models, right? Predictive model, right? You can come up with the correlations, right? Regression-based equations, and then use those regression-based equations, and then use an optimization solver and come up with an optimal solution. Doing all this, you can see here the baseline thickness T1, T2, T3 is so and so and 19 kg, and now RSM based solution gave 15 kg. There is a considerable reduction in the weight of the structure if you consider these three components, right? Bumper beam, rail, and shotgun. Now, with this background, I will compare this method with the practical MDO, right? What practical MDO does is it doesn't create any response surface, right? What it does, within the design space, we populate 175 design cases, right? Let's say we populate. And for these 175 design cases, we do NVH first because NVH is a linear problem, right? And now what we do, we apply the NVH constraints and we figure out those which are meeting the NVH constraints. We list out those which are meeting the NVH constraints. Then when we do that, once the NVH constraint is met, then we run a durability analysis, which is also a fairly linear problem. And once you do a durability analysis, and if the case meets the durability life, right, then we do crash analysis. And after doing the crash analysis, if it meets the crash requirement, then we stop there. If it doesn't meet the crash requirement, then we go to the next step. Do the durability, then do the crash. So what happens is, right, there is no response surface. There is no need to run the crash analysis for all the DOE points. What you essentially do is, you essentially are first sequentially NVH, durability, and then crash. And then you are minimizing the crash runs from 107 to just 7 runs. Right? So how do you do that? So the 7th one is meeting the requirement. So what happens is, the optimal solution, if you see 16 kg, right, from the baseline. So what happens is, if you compare the solution accuracy, right, and the time required, the left-hand side, you can see the optimal solution is more or less close, 15.61 and 16.07 kg. And the time required to run the, come up to this optimal solution, if you see 62 hours and 14 hours, there's a drastic reduction in the computational time, right, in the practical MDO, which doesn't use any response surface. This is one. Now, so there is a 1/4 computational time reduction. Let's say full vehicle analysis is taking 1 month for running all the DVPs. Now, if you apply this practical MDO, only 1/4. 1 week you can do instead of 4 weeks if you apply practical MDO. Now we will see how hybrid MDO is getting. So hybrid MDO, what it does is, it's a combination of practical MDO. That means you do NVH first, durability, and then crash. Along with that, what you do, even for those few crash analysis, you use an algorithm, equivalent static load method. Right? So what it does is, it converts the nonlinear into linear. Right? It will calculate the equivalent static loads, right, which are creating the same displacement field. Then it does the optimization in the static, linear static response optimization. Then it will go back and map to the nonlinear domain. And this is very powerful. And Genesis is the tool. And OptiSign Technologies in India is driving this particular tool. So this is having huge benefit in terms of time saving of full vehicle analysis. Now, so we have seen RSM, we have seen practical, and we have seen the combination of practical and ESL hybrid. Now let us see how machine learning based MDO can help, us in getting solutions, optimal solutions in a very short time. So slightly I took a little complex problem. Like here we have thicknesses corresponding to many parts, many components in an automotive structure, T1, T2, and so on up to Tn. This is the thickness range. And objective function again is minimization of the mass, because we are talking about lightweighting. And then we have constraints coming from IHS offset requirement and natural frequencies of the structure for NVH, and the damage, the maximum von Mises stress on the component should be less than so and so value. Right? So now with these constraints and with these design variables and with this objective function, right? So if we try to solve this problem using machine learning based methods, so how we should go about? So before going to the actual problem solving, I would like to spend 1 or 2 minutes on how these constraints come, right? What kind of experiments we do to come up with constraints here, right? So let's say, right? Let's say you are coming up with a EV platform and you want to convert an ICE engine to EV platform, right? We do experiments, right, on a X vehicle, right, which has a motor, right, and then replaced with an IC engine. Right? What we do is we put microphones and we try to get the noise levels, and we run at different speeds and try to see what is the noise levels at different speeds for IC engine version and for an EV version. And then we find out if there is any potential to reduce the stiffness of the structure in an EV version, right, without compromising on the perceived quality with respect to NVH, right? So why we want to reduce stiffness? Reduction in stiffness will lead to substantial reduction in the weight of the structure. So then what we do is we try to change the constraint equations. So this is how constraints with respect to frequency or stiffness targets will go to the algorithm. So a lot of experiments have to be done for each and every constraint, and these constraints are essentially designed very DVPs, which we call DVPs. There will be huge set of DVPs for various domains. And now we have And now we have NVH responses, and now we have crash response, then we have accelerated durability test response, right? So we have formulated a problem, and now we are trying to, from the simulation, we arrive at the responses, we run the simulations at different DOE points, 200 data points, and we get the responses of NVH, responses of crash, and responses of the von Mises stress, because we need the equations for these in our optimization constraint optimization. So once we get the simulation runs, we develop predictive models using various models. So what we see here in this slide is the components which are very sensitive to NVH, durability, and crash. Right? These are the components which are sensitive to all these three domains. Now, for those components, these are the predictive models which came out from the machine learning, and these predictive models will go into your optimization solver as constraint equations, right? And like this, the constraint equations can be many. In this case, we have three constraint equations because we are looking at three domains. Considering these three constraint equations which came up from the predictive model, and this predictive model is based on machine learning, and considering the objective function and the design variables, right? And the design variables which are affecting these three domains, what we saw is the thickness of these various components. Right? You can run the optimization solver and minimize the weight. So there will be, so in this present thing, there is a 20% reduction in the mass of the structural components for IC engine version, and there will be more than 20% weight saving, potential weight saving for an EV version, because what we saw is for an EV version, there is a potential to reduce the stiffness of the structure without compromising on the perceived quality. Looking at the experimental results, right? So this is how. And the last part of my talk today is how dimensionality and volume reduction techniques, right, machine learning based techniques, can drastically reduce the simulation time. Okay, let's go back to what we saw, right? So we saw there are 200 data points in our previous, right, in our previous analysis. So I took crash analysis as the key because I told that crash analysis is very critical, and crash, and if you try to reduce the number of crash analysis, we are in game, we are in business. So NVH and durability are slightly straightforward because they are linear. Now, you take crash analysis, there are 200 data points, and there are 14 design variables, right? And there are various responses. This can be intrusions, right? Now, if you apply these forward feature selection and clustering algorithms, right? Those of you who are familiar with machine learning will understand forward feature selection and clustering algorithms. If you apply these two on this data set, you can come up with 5 data points from 200 and 3 design variables from 14, right, for this response. And then say that if I just consider 5 data points and 3 design variables for that response, I get a predictive model. Right, with this data set, and use this predictive model and compare the results of this predictive model with the predictive model which we got from 200 data points and 14 design variables, and plot here actual versus predicted. Right, predicted is the x-axis predicted is from these 5 DOE points, right, and 3 design variables, and y-axis is from the 200 data points and 14 design variables. So you can see, no, there's a, if you consider 6 clusters, then your error is 15%, so your accuracy is 85%. So if you can use this predictive models, right, and then without running the DOE crash runs for the rest of the DOE points, and then use this and reduce the time. Let's say for this given problem, 133 days can come down to 3.3 days when you really explore the error. Okay, when you try to use the potential of this machine learning algorithms, right, on the data sets which you generated in the past CAE data sets, right? So there is a huge reduction in the time to solve the full vehicle analysis. So we saw what is optimization, what is MDO, applications of MDO. Then we saw what are the challenges in applying MDO, and then what are the benefits of MDO. Then we took a case study and saw various algorithms like RSM-based method, a practical MDO, and hybrid MDO, where we talked about the ESL method. Then we talked about machine learning based MDO, right? And machine learning based MDO, with machine learning based MDO and equivalent static load methods, and focusing on reducing the crash analysis timelines, you can do the optimization problem in few days, right? And this is a disruption happening in, right? And the same thing can be applied to many other domains like CFD and so on. So my last slide is on, if somebody wants to have career in MDO, what all the things he should look for, right? Suppose if somebody is a beginner, right? He should have strong foundation in mathematics, engineering mechanics, solid mechanics, finite element method, of course, computer programming, and then also you should understand an engineering optimization and how to use basic CAE tools for, these are the beginner should get into this. Suppose you already know these things at the college level, right? You have electives and you are perfect in these areas. Then what you can do is you can start getting into working with industries on various problems, right? Pertaining to crash, durability, NVH, vehicle dynamics problems. You can get into engagement with the industries and solve their pain areas, take up their pain areas, and then get into these areas, right? CFD areas. So once, for a practitioner, what is important is he should have breadth in all the domains. Then only he can do the formulation properly. Right? And then you should also get into advanced finite element analysis, because a lot of nonlinear problems, right? Nonlinear concepts are taught in advanced finite element analysis. And you should get into advanced CA optimization tools like Genesis, so on and so forth. Then for an advanced practitioner, what is important is you should try to see, right? How can you come up with various strategies on MDO, right? Mix and match of multiple things without compromising on accuracy of solution and very fast. Can we use analytics? Can we use ML-based models? Right? Those kind of thoughts we should get into, and then develop a lot of case studies in this space. And for an expert, what is very important is, can we front load CAE? Can we front load MDO? Right? Can we use various methods? Because when you're talking about automotive product design at a concept stage, when geometry is not there, metal property is not there, shape is not there, platform structure is not there, right? When everything is gray, it's very important to come up with some methods like beam modeling, right? 1D models, which will quickly do the analysis and give us some decisions based considering all the constraints, right? And then how to come up with a lot of automation stuff in MDO, and how to use machine learning based, how to use biomimicry, and then club with MDO, right? And then this innovation is a concept spoken out by Professor Kalyan Maydev. So innovation is coming up with rules for a multi-object to multi-disciplinary optimization, right? So how do you do that? So those kind of things one can get exposed to. And this MDO can also be used in other industries, like solving supply chain problems, manufacturing problems, sales and marketing, right? All product development companies can use MDO for their problems. So aerospace, medical, agriculture, the list can go on. So this is a very powerful technique, and that's all what I have with me. And thanks to all for listening. And you can contact me on this mail, right? And these are some of the questions which I thought we should have. Hello? Hello? So hello, can you hear me? I think I'm audible. Can I answer some of the questions? Hello? Okay, let me answer a few questions. Can I apply after completing bachelor's degree in BCA? Right? Yes. So, because optimization is very much taught in computer science courses, and you can come up with various algorithms, where parallel computing is required when we are trying to solve these nonlinear problems. And then for your own domain, right, you can apply these MDO concepts. What are the expectations of automotive companies from the freshers just passed out? So the expectations are you are good at those concepts which are taught in your curriculum, and then you have some hands-on. You must have done some projects in your third year, final year as an intern in various companies, and then not only the education and exposure, you must be acquiring a hands-on skills to handle these tools, techniques, and also try a lot of prototyping and participate in various competitions, so that you'll be delivering as soon as you join in an organization. What is the current software used for analysis in automobile industry? So different softwares are used, right, for solving different domains. So current software, so our Genesis is used for MDO, right? So there are various companies coming up with various optimization tools. So Altair has their own tools. Like ANSYS is also coming up with optimization tools. So when you mention MDO field, can I apply after completing BCA? Yeah. Any questions? Hi. How far away do you see a full-on machine learning implementation? A full-on machine learning implementation in MDO. How far away? Davis Anthony. Full-on machine learning implementation in MDO. Full-on. Yeah, very soon we are hopeful to integrate the machine learning concepts for coming up with the. So there is a software called Lunar, right? Mr. Davis Anthony, to answer your question, how far away do you see a full-on machine learning implementation in MDO? So you can refer software Lunar, Lunar. So it's a full-fledged solver where they use a lot of machine learning algorithms, and it will solve the crash analysis problems in few seconds, right? It's purely based on machine learning and predictive models. Thanks. Santosh Kumar. Hi, sir. BE fresher pass out. How should I look for this field? And what are my opinions in getting into this stream? How should I look for this field? See, when anybody is trying to get into an organization, basically he's trying to solve problems. So when he is trying to solve a real world problems, you will have a goal, you will have an objective, you will have a multiple objective, you can have multiple objectives. You will have constraints, and especially in an engineering company, you have engineering constraints, right? So even if it is not an engineering company, you will have some other constraints, right? So how you come up with the mathematical formulations of those constraints, and then systematically capture the entire real world scenario and then come up with an optimized solution. So definitely, even if you are a fresher, this field is very challenging field, and this can be applied to any product or any domain. When you mentioned computer programming as a requirement, which programming languages are mainly used in this field? So Python, see, Python is very powerful and it has a lot of libraries, automation libraries, automation toolkits. So you can use Python. So if you have further questions, you can mail me, and then I'll be happy to. So students and practicing engineers, so I would like to thank you all for your, for listening to this. And if you have any queries on MDO, and if you want to take this as a as your one of the specialization area, feel free to contact me. You can mail me, right? And then I will help you in in the knowledge resources. What are the knowledge resources available in this space? What kind of challenging problems industries are facing in this area? And then okay, so I will just once again share my screen so that you can note down my email ID. So. So please, this is my email ID, srinivas.gunti@mahindra.com. So feel free to drop a mail for any query, and I'll be happy to answer that. Thanks a lot.